Yuki for Organic Chemistry 1, Test 2, Multiple Choice. So we'll start here. The sec-butyl has the alternative name what? So I'm going to do like a parent chain. And then sec-butyl would be 4 carbons, but is attached at the second carbon. It's secondary is another way you can think of that. So when we're numbering a substituent, we always start closest to the parent chain. So there's 3 things here. So this is propyl, so we can get rid of either of the ethyls. And then we have 1 methyl. There's a methyl at the first position, so it would be this one. There's not 2 methyls. If there was 2 methyls, it would look like that. If it was 2,2-dimethyl, it would look like that. That would be neopentyl. And if it was 2-methyl, it would look like that, and that would be isobutyl. Okay, the next one, what is the relationship between the following 2 compounds? So this is a mirror image, and if this is hard for you to see, you can imagine putting your hand thumbs up, and then the mirror image of your hand also thumbs up. Your thumbs both pointing up, like these bromines are both pointing up, is a mirror image. And then if you try to superimpose it on one another, it can't. So hopefully that can help you see. So these are enantiomers, non-superimposable mirror images. Okay, the next one, we're going to try to find the longest chain here. So that is the longest chain that I can find. 1, 2, 3, 4, 5, 6, 7, 8. So octane is the longest chain I can find, so I can get rid of these. Okay, and then I'm going to find the methyls here, here, and here. Or substituents, I mean, is 3 methyls. So this would be, if I number it the way that I have it currently numbered, 3, 4, 6. But if I go the other way, 1, 2, 3, 4, 5, 6. So we can either get 3, 5, 6, or we can get 3, 4, 6. So 3, 4, 6 is better, so we'll go with 3, 4, 6. Next question, which of the following is the correct Newman projection for the following compound as viewed from the indicated bond from the conformation shown? So I like to draw in my implied hydrogens. So for me, I can see this chlorine going up, the CH3 going here, and the hydrogen going here. And then in the back, I have the CH3 going into the plane of the page. So the hydrogen, the implied hydrogen, is a wedge right here. And so that's up and to the left, and then the bromine is straight down. And so we can't change the order of these. So going clockwise, it has to be chlorine, hydrogen, and CH3 in the front. So I'm looking chlorine, hydrogen, CH3 works there. This one has the chlorine in the back, so that doesn't work. Chlorine, hydrogen, CH3 there. Chlorine, hydrogen, hydrogen, so that one's not right. Chlorine, CH3, hydrogen, so that one's not right. So this one, I think, is an enantiomer of the molecule above, so we can't use that one. So we're between 1 and 3. So now we'll look at the back one. The back one has hydrogen, CH3, bromine, hydrogen, CH3, bromine, so that's a good option. Hydrogen, bromine, CH3, so that's also, at least the back one is an enantiomer. Okay, which of the following has the least angle strain? So the closer we get to 109.5, the better. So the larger ring is going to have the least angle strain. Consider the graph below, which is a plot of the relative energies of the various conformations of 2,3-dimethylbutane viewed through the C2-C3 bond. The conformations corresponding to 120 and 140 are. Okay, so when I'm looking at this, the higher energy is, the higher the energy, the less stable it is. So the bigger groups will be closer together. So let's say on butane, we have a CH3 and then, well, it's 2,3-dimethylbutane, so it would be something like this, and then like this, I think would be right. 1, 2, 3, 1, 2, 3, 4, yeah, there we go. So the most stable conformation is going to be where our bigger groups are further apart. So if we had our hydrogen over here, I think that's the furthest apart our groups can be. At least it's only 2 together, where here all 4 of the biggest groups are together. So this is the most stable at 180. And then a position like this would be still, because it's staggered, still stable, but not as stable as the biggest groups opposite from one another. And then we start to get into our eclipsed conformations. So the highest energy eclipsed conformations is when the same groups are sitting right on top of each other. So those would be these, the two highest positions. So what's left at 120 and 240 are eclipsed, but not fully eclipsed. Oh, it's not even asking us like gauche or whatever. It's asking which of these are more or less stable. So we know it's eclipsed because they're higher. Eclipsed and more stable than the conformation at 0? Yes. Eclipsed and more stable than the conformation at 180? No. So it's just asking if you could read stability. Nice. How many chiral centers are in the compound shown below? So first I'm going to get rid of anything that's sp2 hybridized. So I know all those are sp2, so it can't be any of those. This one could have, maybe I'll just highlight all the possible ones. Let's see. All these can't be it because they're all sp2 hybridized. No heteroatoms in this class. So it can't be any of these. Okay, those are all sp2 or heteroatoms. So now I'm going to do in a different color anything that I see that has 2 hydrogens. So 2 hydrogens here, 3 hydrogens here, 2 hydrogens here. So then I just see 1 here and 1 there with 4 different things attached. This one has 2 carbons with different things, a nitrogen and a hydrogen. And this one also has nitrogen, 2 carbons, different types of carbons, and a hydrogen. So I see 2 chiral centers there. Rank the bold-faced hydrogen from most acidic to least acidic. Okay, so there's a few different ways you can do this. I have the pKs of most of these memorized, so I know that this is about -2, this is about 44, this is about 4 to 5, this is about, let's see, the bold-faced hydrogen, this one. This is about 25, and this is about 10. So that's one way you can do it. You can also think about them in terms of electronegativity, like the most electronegative atom here is the oxygen, so those are probably going to be the most acidic when compared to carbons and nitrogens. But for me, it's just fastest because I have the pKs memorized to rank it that way. So the most acidic is 5, so I can eliminate any that aren't 5. Starting with 5, and then the next is 3. 5, 3, 1, yep, and then 2, 4. And I like to check all of them, even though you can get it from less than that, just in case. All right, so let's see, this one, we're looking for a correctly positioned equatorial alcohol. So when I'm looking at chair conformations, and I have a video about this, like how to draw chair conformations, usually at these 4 corners, the axials are going to be pointed alternatively up and down. These are like the standard positions. And then here, this one's down, and this one's, that one's axial up. So those are like the standard positions you'd see. So on a structure like this, I would expect this to be axial up, this to be like this, that one would be up. So you can kind of see like, all right, we kind of have standard positions where things appear. So this axial up is in a correct position, but it's axial, so it's not our answer. This equatorial up is in the correct position, but yeah, it is. So there's no but. So that could be our answer, but I'm going to keep going. This is just a wedge dash, so neither of those could be right. And then over here, this is not in the standard position, so it's hard to tell. We would have axial up here or axial down here or equatorial up. Being axial up right there isn't one of the standard positions. We should have axial down. So that's not correctly positioned. So answer choice B is our answer on this one. Next question, would this ring be considered cis, trans, both, or neither? This is considered trans because one's a wedge, one's a dash. Okay, the next one, Cymbalta, has a chiral center. Assign the absolute configuration of the chiral center as R or S. So let's see. First, we have to find the chiral center. So again, I'll go through, and anything that's sp2 hybridized, we know can't be our chiral center. So none of this can be a chiral center. And we also know our heteroatoms are not chiral centers. Then I'll get rid of anything that's got 2 hydrogens for sure in it. Oh, and then our one chiral center also is the only place that has the 3D structure, so I could have noticed that, but I didn't. Okay, so now we're looking, I'm going to erase all this so that way it's easier for me to see. Now we're looking at the chiral center right here, and first I assign priority. There is an implied hydrogen that is a wedge pointing directly towards us, so that's the lowest priority. And then we have a carbon, oxygen, and another carbon. So between these three, oxygen is the heaviest. So this would be 1. And then between these two, we have 2 carbons. This carbon is attached to carbon and then 2 hydrogens. This carbon is attached to 2 carbons and a sulfur. So this one wins. So this would be 2 and 3. So 1, 2, 3 is pointed to the right. So that's R. But because our hydrogen's pointed directly at us, I would choose S. Okay, the next question is, would the following reaction happen? So this is an acid-base reaction, and the question is, will the reaction happen as favored? So like, would this forward reaction happen? Now, I intended for this to just be a one-way arrow, so I made a mistake on this question, and there's a typo in one of the answers. So we actually accepted 2 answer choices on this one. But essentially, would this even occur? And is what we're looking for. So with the nitrogen here, would this take it and go that way and give us, oh wait, no, sorry, the other way. Yeah, oh no, that's right. The nitrogen take this, and we get OH minus. So this is an acid-base reaction. How can we tell which side is favored? You typically look at the pKa and determine the acid, which is here, and the conjugate acid. And then you compare the pKas of these, which one's more acidic. Now, oxygen is typically more acidic than nitrogen because it's more electronegative, but you can also compare the pKas. The pK of this is about 15.7, and the pK of this is about 38. So between these two, this side would be favored. So this forward reaction really would not happen. So that's what the question is asking, is would this reaction happen? Sorry, my brain just short-circuited. Should I start the video over? No, I think I'm just going to leave it. I was focused on trying to explain the mistakes that I made, and the larger side is favored. I don't know why I just did that. So the reaction would happen. I don't know why my brain just didn't work. The larger, weaker acid is favored. So the conjugate acid is the bigger pKa. So it is less acidic, so it's more stable, less reactive. So this side of the reaction is favored. I don't know what's happening. So this side of the reaction is favored. So none of the ones that say no are possible. The reaction would happen, and it would be even favored to go forward. So in all these, if you're looking at their no is wrong, so you can eliminate them, but also water wouldn't give up the proton because the resulting conjugate base wouldn't be stabilized by resonance. Well, you can have acids that aren't stabilized by resonance, so that doesn't make sense. The next one, water would give up a proton. That doesn't really make sense because water would give up a proton and the reaction would happen. Next one, no, water would not give up a proton because water and nitrogen have 2 bonds. That's not a reason that makes sense, it having 2 bonds. So we get down to these two, either of these two. The first one, yes, water would give up a proton because the resulting conjugate base would be stabilized by resonance. Well, there's no resonance stabilization, so that one doesn't make sense. So the very last one, water would give up a proton because the resulting conjugate acid would have a negative on the more electronegative oxygen. This should be the resulting conjugate base would have a negative on the more electronegative oxygen. So that's a different way of reasoning than we've used before. But it would ultimately be the more stable product is favored, and the negative being on the more electronegative atom is better. Makes it more stable, makes it less reactive. So it's something you've seen before, but it's applied in a slightly different way. And the reasoning isn't word for word something that we've talked about, but it is reasoning that you've seen before. But I didn't want to trick you. So what I did for this question, and I looked at the, the breakdown of how people answered. Because I had a typo and it was, my mistake, I basically just wanted to make sure, did you know that yes, essentially this reaction would happen, that you would have the acid-base reaction. So I accepted either of those, even though the resonance stabilization didn't really make sense, and like well over the majority of the class got that right. So that's usually what I'm looking for. Is it like 75% of the class got it right? Then that's worth it. So I ended up just accepting 2 answers on that one. Okay, the next question. The preferred conformation of trans 3 tert-butyl 1 methylcyclohexane. Okay, so I'm going to do this a few different ways. First, we know that all of the things pointing up are rotating. Axial, equatorial, axial. They're alternating axial, equatorial, right? So if I have something that's 3, 1, and it's trans, then I'm just going to pick equatorial for one position. And then the next position would have to be axial. So we need one group axial and one group equatorial. Now there's 2 groups here, a tert-butyl group and a methyl group. So the tert-butyl group is much bigger, and we prefer the bigger group to be equatorial because it has more space. That's something we've gone over in class a few times. So they can't both be axial, they can't both be equatorial. The boat conformation is not the most stable, chair is the most stable. So it'll only be A or B is what we're looking for. And between these, the tert-butyl group being axial is less stable. So we're going to go with the tert-butyl group being equatorial. This next question, I also made a mistake. I didn't check all the answer choices well enough, and I did not realize that these 2 were identical, but one had a 1 and the other one didn't. So let's go through and name it, and then I'll tell you what I did. So when I'm looking at this is a 6-membered ring, 1, 2, 3, 4, 5, 6. So this is cyclohexane. And then at position 1, we have the alcohol, so 1-all, and then position 4 is a chloro. So combining this all, we would have 4-chloro, cyclohexane, and you can technically just write all because it's a ring, so you don't have to put 1. That's a IUPAC rule that I disagree with, but hexane, either of these is I would accept, but technically this is the IUPAC name. But I told you guys I would never test you over that. And I did not intend to test you over that. I liked this question because it was naming from the chair conformation, and I thought that would kind of challenge a few different things for you for trans and cis. But I did not realize that this question, the test bank was testing you over that. And so there's 2 answers that went with what I said I would do in class. And I really try to stick with what I say in class. So I did make a mistake, but I would accept either of those. We definitely don't have the 4-all. So that narrows us down to trans, or cis. And between these 2, we have 1 pointing up and 1 pointing down, so it's trans. So I accepted A or B. So if you did A or B, and actually one person wrote on their test booklet, both are same, and picked E. A and C are both the same, so E's the right one. So I actually accepted A, C, or E on this question because of my error. I just only didn't accept the 2 that said cis because I wanted to make sure that you could tell that it was in cis conformation. So I just wanted to let you know, just out of an abundance of trying to be fair, that's how I did that since that was my mistake. Okay. And I will say, if you spent time worrying about that in the class, something you can always do is raise your hand and ask the question. And if there's something like that doesn't seem fair, if I explicitly told you I wasn't going to test you over it and then I test you over it, please know that I'll try to do everything I can to make it right. So don't spend time worrying about that on the test. Move on to ones you're sure about and then come back to that. And just go with the best thing that you can. Okay, catalytic hydrogenation of which of the following would yield 2-methylpentane? So I'm going to draw these all out. A is 2-methyl-1-pentene. B is 2-methyl-2-pentene. C is 4-methyl 2-pentene. D is 4-methyl 1-pentene. So I numbered all these starting with the number 1 on the left. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So if these go through catalytic hydrogenation, which is just hydrogen with a metal, platinum, palladium, or nickel, it just deletes that double bond. I'm going to redraw all of these. So if I redraw all of these, now I'm going to number them and rename them. 1, 2, 3, 4, 5. And I'm going to start to make my substituents as low as possible. So all of these are 2-methyl pentane. So that's just something we talked about very briefly at the end of chapter 4. This reaction, and it essentially just deletes the double bond. And I had some people ask, like, well, once a reaction happens, can I change the way I number the ring or the molecule? And yeah, once a reaction happens, you get a new molecule. So this is a new molecule, so you name it through IUPAC standard naming. Okay, so that is the multiple choice. So there's a few of those that we accepted multiple answers on. I think that I mentioned all of them. Okay, and then now we will do the free response. So this question from the free response was taken very similarly from the review. So if you're like, we haven't seen something like this before, make sure that you're doing all those things in like the review. You're going over old free response questions. So part 1, we're drawing out the molecule CH3CCH. There's a triple bond in there, and the molecule NH3. Part 2, we're drawing curved arrows to demonstrate an acid-base reaction between the two molecules. So you have to figure out which of these is the acid and which one of these is the base. And typically the pKa of a carbon-carbon triple bond is about 25, and the pKa of an amine is 38. And now carbon is less electronegative than nitrogen. So you might think that carbon is more acidic, because as we become more electronegative, it becomes more acidic. But you also have to take in consideration hybridization. And so if it's not like a sp3 hybridized carbon, you can't do the direct comparison like that, because hybridization starts to change it. And so here are the curved arrows. It looks like this. And this would be the products. So I did part 1, I did part 2, part 3, predict the products, I did that. Part 4, circle the side of the reaction that's favored. So to do that, we're going to compare the acid, which in this case is the carbon-carbon triple bond, and the conjugate acid. And the pK of this is like 10, so actually this side of the reaction is favored. Okay, for the following molecule, assign each group priority. Okay, so this is priority 4, and now we're looking at all 3 of these carbons, and I saw a lot of people, we talked about this actually in class Thursday before the test, and then it happened on the test on Thursday. Most of you knew that the hydrogen was priority 4, and this carbon having 3 hydrogens on it is priority 3. But we really have to compare all 3 of these, because all 3 of these are carbon, so any of these carbons could be, the next priority. So we have blue, green, and orange. Purple is definitely priority 4. So blue, green, and orange are all carbons, right? So now in blue, we look at what it's attached to, and it's attached to 2 hydrogens and another carbon. Then green, we look at what it's attached to, 2 carbons and a hydrogen, and then orange, what is it attached to? 3 hydrogens. So all of them have at least 1 hydrogen, so they're all equal there. Then we get to the next level, hydrogen, carbon, hydrogen. Green is the only one that's different. It has a higher priority. It has a carbon, so this is number 1, priority number 1. And then now we're comparing blue and orange. So blue now would be priority 2, and orange would be priority 3. So if you're looking at these, all 3 of these are carbons, and then this one has 3 hydrogens on it. This one has 2 hydrogens and a carbon, and this one has 2 carbons and a hydrogen. So 2 carbons is more than 1 carbon. 1 carbon is more than no carbon. So that's how I got blue to be priority 2. and I've talked about this a few times, you don't take the weight of the whole chain, you take the weight of the first point of difference. That's what you're looking at here. But even if you took the weight of the whole chain, this has way more atoms. So actually I think this one would end up being heavier. But I saw a lot of people put blue automatically as position 1 and green is actually position 1. So let's see, this would be, I already lost track. 1, 2, 3. So this would be our configuration. Now what we did is if you swapped 2 of them and you put S configuration, we counted it right. So if you put the right order here and you put R, then you got full points, all 5 points. If you put the wrong order here, you got 2 points off here, but as long as your configuration matched with what order you thought it was, you got 3 points total. Like if you said that it was, if you swapped blue and green, which is what I saw most people do, then it would be S configuration. And so we gave credit if you put S at the bottom, as long as you swapped blue and green, because that was consistent with your early answers. So it's kind of like, we don't want you to be deducted points twice for that one mistake. And then even if you put this in the wrong order, if you still got R, then we gave you credit for it. So we try to give as much points on that as possible. Okay, next question. In your own words, describe why cyclohexane prefers chair conformation, not a flat hexagonal shape. Use complete sentences to put together a coherent explanation. So cyclical molecules in a flat shape have ring strain, specifically angle strain and torsional strain. This is something that I'm looking for, a complete sentence. So cyclical molecules, if they took a flat shape, have these types of strains. By bending out of the plane, that strain can be minimized. So cyclohexane adopts a chair conformation primarily to get, to alleviate torsional strain. Ring strain is less of an issue with cyclohexane. A ring strain, less of an issue with cyclohexane. It gets closer to 109.5 than any of the other ones do. So it has a better angle on it. But as long as you mentioned ring strain, which is made up of angle strain and torsional strain, and or like explained that in a way that made sense, we gave you credit for it. If you communicated that ring strain wasn't, or that angle strain wasn't as important as torsional strain, that's totally great, but that's not necessarily what we're looking for. So I believe you got a point for having coherent sentences and talking about ring strain and torsional strain in a way that made sense. Okay, draw the following molecule in a sawhorse from the Newman projection. All right, so I like to do this by saying we have 1, 2, 3, 4, 5, 6 carbons. So 1, 2, 3, 4, 5, 6, right? 1, 2, 3, 4, 5, 6 carbons. So the first carbon is just CH3 right here. Second carbon has an alcohol pointing up and to the right. So we could actually probably just do this straight up. We don't have to draw in the hydrogens if we don't want to, but you can. And then the next one we had, let's see, we just have 2 hydrogens, and then that's it. So I think what we did was we gave you a point for the parent chain, and we gave you a point for having the alcohol in the right position, and a point for the right configuration. So like the alcohol coming towards you, or if you drew it this way. The alcohol being away from you, whichever way you drew it. So that's what those 3 points came from. Okay, I had a few people come into my office after this test and talk about how they were disappointed because their grade wasn't as good as it was on the first one. And I just want to say that I know if you put in a lot of work for the first exam and then you got a good grade, and then you put in the same amount of work for the second exam and you got less of a good grade, the material did ramp up a little bit. And so it's like more challenging material, and it's brand new, not things you've done before, whereas the first one is all stuff that you've seen before, or mostly stuff you've seen before. So I want to encourage you that it's okay and it's not the end of the world, and just take this as a learning opportunity and see how you can adjust your study techniques for the next exam. But don't be too hard on yourself, and remember, we get one dropped exam grade. So I hope that helps, and I hope that you're not too disappointed, and I'll see y'all in class. Good luck studying.